In this video, we will discuss how secants in geometry can be used to approximate slopes of tangent lines. Slopes of lines are just fractions involving the vertical rise divided by the horizontal run. The fractions associated with lines formed by secants happen to be linked to fractions associated with tangent lines by a natural limiting process. It's an amazing fact that under certain conditions, we can understand and control the behavior of approximations that occur, producing very precise outcomes. This leads us towards formal definitions of the derivative in terms of limits of fractions, which is the main idea in this video. The underlying idea of calculus is to use tangent lines to approximate smooth curves. Lines, of course, use simple arithmetic. So if we can use this, then there's a substantial reduction in complexity, and we have the possibility of creating some very powerful and wide-ranging tools. A tangent line, typically just glances a curve at a single point of interest and acts as a good approximation to the curve near this point of intersection. To try to understand what's going on, let's carefully analyze the simplest quadratic of all, y equals x squared, and see if we can extract some general principles. Note that we're reverting x again as the independent variable and y the dependent variable. A typical point on the curve has coordinates x on the horizontal axis and x squared on the vertical axis. And we can draw a tangent line to the curve passing through this point. We can alter the x input slightly simply by adding h to get a new input, x plus h, and then move up to the curve and across to the vertical axis to land at the value x plus h all squared. Hence, the new point on the curve has coordinates x plus h and x plus h all squared. We can now join these 2 points on the green curve with a straight line segment colored blue in the diagram. A line that joins 2 distinct points of a curve is called a secant in geometry. Because it's a line segment, this secant has a slope in the usual sense. That is a vertical rise divided by a horizontal run. You can see that the horizontal run in the diagram is h. And there is no harm throughout this discussion in assuming that h is positive. The vertical rise in this diagram is the difference in the y coordinates, namely x plus h squared minus x squared. We'll look at the quotient of these carefully in just a moment. Note that as h is made smaller and smaller, approaching zero, without actually reaching zero, the slope of the secant approaches the slope of the tangent line. And it's conventional to use these arrows as abbreviations for the word approaches. To see this visually, imagine the second point slipping or sliding down the parabola towards the first point. Even though the secant gets shorter and shorter, the direction of the secant aligns more and more with the direction of the tangent line. The result is that their slopes look like they're going to coincide, and we think of them as actually coinciding in some kind of limit. Note that even though h approaches zero, it doesn't actually reach zero, as these diagrams require two distinct points in order to form a secant. If h were equal to zero, then there would be only one point on the curve, not two. So returning to the earlier diagram with horizontal run h and vertical rise x plus h squared minus x squared. Let's look at the quotient representing the slope of the secant. The numerator representing the vertical rise can be expanded, and then there's some cancellation. So the fraction becomes 2xh plus h squared divided by h. And the numerator factorizes, and the h cancel in the numerator and denominator, simplifying further to 2x plus h. As h gets closer and closer to zero, this expression 2x plus h for the slope of the secant gets closer and closer to 2x. We've derived this very important result, that the slope of the tangent line to the parabola y equal x squared, and the point of the coordinates x and x squared is just twice x. Now, if we go through the same process with y equals kx squared, where k is some fixed constant, then the previous calculation simply gets scaled by a factor of k, and we'll get the following result. The slope of the tangent line to the parabola y equal kx squared at the point with coordinates x and kx squared is just twice kx. We can now discover a surprising connection with areas of circles. Consider a circle of radius r. Its area, capital A, is given by the formula pi r squared. The perimeter, capital P, is given by the formula 2 pi r. That is twice pi r, which is precisely the slope of the tangent line. So the parabola A equal pi r squared at a point with coordinates r and pi r squared, where we interpret our previous result using r for x, capital A for y, and pi for k. This isn't a coincidence. It's an instance of something quite profound in mathematics. Forming slopes of tangent lines is called differentiation. Finding areas of region in the plane, like finding the area of a circle, is called integration. There's a remarkable connection between them described in the last module of this course called the fundamental theorem of calculus. Something as innocent looking as a simple relationship between slopes of tangent lines and areas of regions in the plane turns out to be one of the most transformative observations in the history of mathematics. And was first noticed by Newton and Leibniz in the 17th century. The idea behind the calculation we just did for y equal x squared generalizes to any smooth curve y equal f of x. Choose some point of interest with coordinates x on the horizontal axis and f of x on the vertical axis. Now attach a tangent line to the curve that passes through this point. Now alter the x input slightly by adding h to get a new input x plus h. The output corresponding to this new input is f of x plus h marked on the vertical axis. We now join the 2 points on the curve to form this blue line segment called a secant, as before. In moving from the first point to the second point, the horizontal run is h and the vertical rise is f of x plus h minus f of x. So the slope of the secant is the quotient of So the slope of the secant is the quotient f of x plus h minus f of x divided by h. The slope of the tangent line is the limiting slope of the secant as h tends towards 0. You can see this visually as a new point slides down the curve towards the original point. The secant gets shorter and shorter and shorter. We capture this idea using this limit notation. LIM is an abbreviation for limit. And together with h arrow 0 beneath the full result reads, the slope of the tangent line is the limit as h approaches 0 of f of x plus h minus fx over h. Whatever this limit evaluates to, representing the slope of the tangent line, is called the derivative of f at x. This technical expression involving limits has several equivalent formulations that we'll explore more in later videos. However, it's quite astonishing, as you'll see, that we're able to calculate and control these limits precisely with many different functions f. In this video, we considered in detail the process of taking the limiting slope of a secant to find the explicit formula for the slope of the tangent line to a parabola. The underlying method generalizes to any smooth function and is the basis for formal definitions of the derivative, which we will discuss in more detail in other videos. The idea has two main ingredients: forming slopes of line segments, which are special kinds of fractions, and then seeing what happens in the limit. Because of the importance of the idea of limits, we'll discuss them in more detail in later videos. Thank you very much for watching, and I look forward to seeing you again soon.